Nice. Okay. All right. Let us start today's member seminar. It's an honor to have Professor Babak Haghighat, who is both at Tsinghua YMSC and BIMSA, who is going to talk about topological defect lines and topological quantum field theories. Yes, thank you very much.
Okay, you all hear me? Good. So thanks a lot for the invitation and the introduction. It's a pleasure to give a talk here. And as I understood, the talk is supposed to be, very introductory, so that everyone can kind of follow it, because there are people from many different fields, the way I was told. So I hope this is going to be fine. So let's see. So the talk is about topological defect lines and topological quantum field theories. And I will be, of course, these objects, one can define them in many numbers of dimensions, but I will be focusing on so-called 2D and 3D theories. So let me begin with a couple of pictures about, first of all, about topological defect lines in 2 dimensions. So what do I mean by this? Let's come to that. So first of all, here you see a couple of pictures. So there is a line in 2 dimensions. So that's as much as I promised, right? So that's of course just a very superficial level of viewing these things, but more specifically, these are objects in so-called 2-dimensional CFTs. So the CFT stands for a conformal field theory, which is a special instance of a quantum field theory. Let me just briefly explain, because there's not so much familiarity with quantum field theory. So what are these quantum field theories? So let's take this 2-dimensional theories. You can think of them as some, if you want, some statistical models. So there are some degrees of freedom on this 2-dimensional space. You can think of it either as a lattice. You can have some spins up and down, and you can have some, weight function, and you can take the statistical sum with that weight function. It gives you a number. That number is called partition function, and that's basically, one way to kind of categorize these quantum field theories. And these line defects in that language, which I just described as kind of the statistical models, they are certain boundary conditions. So you can, if you have, for example, this spin model, where you can have on some lattice some spins pointing upwards or downwards, and you sum over all configurations and so on. This line here just means that when you cross this line along this line, you just flip them. So that's for example, one type of line, right? So one. Exactly. That will be an operator which just flips it. For example, sigma x will do that, right? So that is kind of a kind of intuitive way to think about these. But more generally, mathematically, what we are talking about here are so-called topological lines. So there is a very special property that these lines, they of course will change your partition function when you insert them on your 2 manifold, but they're topological in the sense that this change doesn't depend on the shape. So you see, I have deformed it, but the result will be the same. So this is kind of what we mean here by topological. So as long as you just deform it and don't do something too fancy, everything is invariant. That means that, as I told you, you can compute, for example, the statistical partition function and it will be the same. That number will be the same.
Because you're adding over all possibilities.
You're adding, and also these lines which you put there, they act in a certain way on the theory. Not every line is topological. They act in a certain way. They're physically they're equivalent. Yeah. Right. For example, yeah, that's another example. Right, right. So another more, maybe from a different point, more intuitive way to talk about these is that you can think of them as, yeah, so devices acting on certain vector spaces. You see, I've put here a point. This point is in physics is, let's say, an operator. And this is an element of some vector space or Hilbert space. And this line defect, it basically acts on this as like a machine acting on this vector space, giving some, you act on some element, gives some other element. Okay, you can think of them also in this way. And the way it acts is because it's topological, you can just shrink it. You shrink it and it acts on it and it gives you a different operator, which is the action of this line operator on this, yeah, on this point, right? So this is basically what these are. I mean, as much as I can say, I mean, of course, there's much more to say, but just to give you a first order definition of these. Okay, let me proceed. So another important property of these lines is that they satisfy certain fusion rules. So they form, in other words, they are objects in an algebra. So you all know maybe what an algebra is. You have certain elements of some space and you take products of them and give you some combination of some elements. So these n's here are the coefficients. They can be either 0 or 1. So you get a sum of other lines. So here you have an example. You put one line here, another line here. You bring them close to each other. You get a third line. And basically, they are all equivalent. That's what this rule here says. Physically, these configurations are equivalent. And moreover, they can also form junctions. So you can have lines here, two lines basically joining and forming this third line here. And this is called a junction configuration. And the allowed line here is basically again given by this algebra. So this is from that point of view now, okay, you can again ask how is this realized in the statistical model and so on and so forth. That's more complicated. We don't have time to say all this, but we can definitely remark that there will be objects which will form these types of algebras satisfying these kinds of relations here. Okay?
Can I ask you a question?
Sure.
When the LA and LB come together, so if I think of this two-dimensional square as a lattice,
yes,
and if I think of blue line and the red line as the ones that flip the spin somehow, sure. You're saying that when I'm adding all possible spin configurations, drawing red and blue is the same as deleting them and drawing the green, but with those coefficients.
Exactly.
And adding.
Exactly. Sometimes you get sums of things. So then you have to add, let's say, a green one and another, let's say, yellow one or whatever. You have to, if you, for example, if your task is, you can do many things. If you want to compute partition functions, you have to add them and so on. So.
Now, the partition function is just going to be a sum over all configurations, so it just gives us a number. I don't see where the Hilbert space there.
Oh no! The Hilbert space, as I said, is when you can put a local, so-called in physics we call it a local operator on this plane, right? This can be for a given quantum field theory or CFT or whatever. This is element of some vector space, a Hilbert space. So you can put it there. That's another degree of freedom which you put there. And then you can take this line operator and contract it. Then it will produce, let's say, another operator here.
In the first picture,
yeah.
What if you act on spin configurations? I understand the flip, but then it will not be. If you act on the partition function, that's one number. So what is L here? It's not acting.
No. And for our purposes, No, but well, the top picture is clear. You have basically an operator here, and you can deform it. Okay, let's put it this way. It is acting on degrees of freedom, microscopic degrees of freedom in this quantum field theory. But let's focus on this part. Maybe this definition is more mathematical, intuitive. It will act on this kind of operator, which is in some vector space and gives you something new. Now, if you deform it, the action is still the same. You can make it wiggly and so on. The action will produce you from one element, it gives you another one, right? An operator on some vector space, right?
Can I
Yeah.
say something which is my understanding of what you're saying? In both of top picture and bottom picture, this thing is acting on a vector space.
Absolutely.
However, in the top picture, it changes the vectors as points in this vector space. After changing it, you can calculate the number associated to the modified lattice. And that number he's saying stays the same.
Right.
Yeah, exactly.
Yeah. But anyway, let me maybe continue. Yeah. So you can basically what I told you they will form an algebra. So more generally, they will form actually a so-called fusion category. And an important example is this Tambara-Yamagami category. So what does that mean? You have certain line operators, as before. They are labeled by some elements of Zn. This is some abelian group, and you take now the fusion of two, and the resulting object, which I called before, this LC, the green one, is just the one which is basically A plus labeled by A plus B. And the addition room is the one, the group law for the Zn here, let's say. Now, this is, of course, just a group law, but then what makes it to a category is that you have another type of very special object, is Lx. And this is called the duality defect, which kind of stays invariant under the action of all the other ones. But when it is fused to itself, it should put here. So when it is fused to itself, it gives you a sum of all the others. So this is kind of a very special rule. And these objects, as I said, form a abelian group. And these guys, these Lx's, do not form a group structure, because you can see there is no inverse element. If there would be a group, there would be some Lx inverse, which you could multiply from the right or from the left, such that you get the you get back, this object, but it is kind of non-invertible in this sense, that you get the sum of these guys. So this basically defines the structure of this category. And an important example is the Ising model, which I described before in terms of the statistical kind of model. And here you can have several lines. So there is the identity line, which does nothing, right? But then there is this other line, L psi. This is the one which I described before. This is the one which basically is in the statistical model is just sigma x. It flips all the spins along some line. And these two form a Z2 subgroup, because if you flip the spin once and flip it again, you're back. So you get the identity, nothing happened. So they form a Z2 subgroup, but then there is another one, which is non-invertible, in the sense that, yeah, this is the so-called the duality defect. If you fuse it with itself, it gives the sum of these two. So this one is very special. It's more complicated to explain where it comes from, so I will leave it like that. I will just state here these fusion rules as a definition. So one can, of course, define it again in the statistical model and go into many details, but that would be a talk for itself. So that's why it's hopeless to kind of do that. We just, take these rules as a starting point. And this is called Ising. That's what I say. This is another type of defect, which is similar to the spin flip, but acts in a more complicated way on the statistical model. If you want the microscopic, so there are two things. I give you two perspectives. There's this microscopic one, and there is the one which is basically, the action on these operators, or as Sergio said, taking the residue and so on. So they are both eventually the same, but the microscopic one is also defined away from the CFT point, just on some lattice, and you can define it as an action there. Yeah. Mm-hmm. Sure. Sure. You can do it. Yeah, you can do the Ising field theory, the conformal CFD corresponding to certain operators and so on. But you can also do the same definitions on some lattice, some statistical model. It's at the end all the same. You can do both. Well, maybe. Yeah. Yeah. I mean, you're familiar with Ising model? Okay, perfect. Then, so for example, there's a duality there, right? But you can also define it on a lattice and let it flow to the continuum, and it's there. If you're familiar with Ising model, you know about the duality of the lattice, the dual lattice with the inverse coupling, right? So you can actually put on half of the space the actual theory. On the other one, you put it on the dual lattice with the inverse coupling, right? Then you go at the self-dual point of the coupling. Then that's that line. That's how it is defined. Yeah, you can define it in this way. It adds some signs in the transfer matrix. Yeah. Yes. No. Well, many theories will give rise to the same type of algebras or categories, right? But they can be different. So, but in the Ising model, you can either do the continuum field theory, right? Or you can start from the lattice model. You can define all these operators in both ways. That's totally fine. And they will form this algebra. But there could be some other theories which give rise to the same thing. This is just one example. Okay. So now another important ingredient is that you have this F matrix. So if you have, say, you see these lines, they can form trees, right? You can take A and B, they fuse to D, that fuses to C, and so on. Say this last guy is just a vacuum, the transparent line. Then you see you can have this tree, and then you can take this leg, this B leg, and attach it to C, as done here, right? And these configurations are equivalent up to the action of this kind of matrix called the F matrix, which sums over E, and yeah, it's basically, again, acting on these vector spaces, if you want. So it's a matrix transferring between different trees and gives you equivalences between physical theories with different trees. Okay, so that's another thing. Now, these F matrices have to satisfy certain identities for consistency. It's called the pentagon identity. That means that if you start, let's say, from this kind of tree, you attach the leg 3 here to the leg 4, and then leg 2 to the, again, here, and so on, or you follow the other path down there. At the end of the day, this has to commute. This has to be basically consistent, you can go this path and all the way back to itself. So this means that the product of all these F matrices should give you the identity eventually. This is called the pentagon identity. And for the example of the Ising model, where you take the sigma lines, the duality lines as before, I've kind of drawn this example. So here you have to sum over this A, which is either 1 or psi, so either nothing or the spin flip defect. and you're summing here over these A's here, which can be these guys, or you sum over sigma here. So again, for this particular example, the product of all these matrices has to be kind of giving you some identity, and this gives you constraints on these F matrices. Sometimes these constraints are strong enough to solve them fully, and you need them to kind of, yeah, pin down your theory. So that's another data point which you need for this kind of structure. So the structure automatically gives rise to these F matrices and these identities. So it's just self-consistency, if you want. And yeah, here, whenever there are these indices along these legs here, they're meant to be summed over. So the external ones, they're all fixed. Those are fixed, but these guys, the C, D, and so on, they are all meant to be summed over, as written here, right? This E is summed over. So that's kind of how this is understood. Yeah, you can give explicit examples for Ising model, for other models, and so on. Mm-hmm. Mathematically, yes, exactly same thing. Yeah, that forms a structure of monoidal category, and yeah. So that's what I wanted to say so far about 2D. Now we are going to uplift the whole structure to 3D. So now many interesting things will happen. So 3D, by 3D, I mean that we have two-dimensional space, and you can have particles there, yeah, and then you add time. Then they can move in time and so on. So let's see what happens. So in particular, I will be interested in a three-dimensional topological quantum field theory. Everything is again topological. So it means that you take the partition function of this guy on a three-manifold. The result will only depend on the topology. In this case, so that's why it's a topological quantum field theory. In this case, my three-manifold is not taken to be a closed manifold, but it has a boundary. So now the path integral will not produce a number, but because there is a boundary, it produces a vector in the Hilbert space. This is called the wave function. And this is basically, and it will only depend on the topology because it's a topological quantum field theory. And depending on what quantum field theory you put on what three manifolds with what boundary, you get a particular Hilbert space and a particular state there. Now, what you want to do is you want to add some particles. I don't know whether I should maybe as an intermediate step draw some picture here. So you can take this boundary, right? And you can add certain particles. In physics, you have, of course, particles or operators and so on. But then they can, if you have here time, you can trace them back in time. So they will be becoming lines inside this three manifold. The whole structure will be forming some lines ending on certain points. So now I want to add these particles in the physics of the story and then compute the corresponding vector in this Hilbert space. So what is now happening? Now several crucial things happen, and I want to explain this by first recapping the situation in 3+1 dimensions. So in our normal world, where we have three spatial dimensions and one time dimension, we can have two particles, fundamental particles like electrons or whatever. And now you take one and rotate it along the other, right? So this gives you rise to this will give rise to an action on your wave function, of your two-particle wave function. But this loop here, you see, since you're in three dimensions, you can take this loop, you can take the path, and you can slide it out so that it actually does not encircle the particle. The particle is left outside because you're in 3D. You can just, take it out. And that's kind of these things are topologically equivalent. And so this wave function, when you do this operation, you'll get an action on this wave function. But this action, because of this topological equivalence, it means that when you go once around, nothing happened because it is equivalent to this guy. So this is exactly equal to the previous configuration. So the wave function shouldn't change. So therefore, when you just exchange them, you don't go all the way around, but you go halfway around, right? You just exchange them, then you can have either plus or minus signs, because only these cases will give you at the end the identity when you do twice exchanging. Twice exchanging is basically going once around here. So therefore, the particles can be either, let's say, bosons or fermions. So either nothing happens to this wave function or they pick up a minus sign. Now, this is the situation in 3 plus 1D. We are interested in 2 plus 1D because we're going to add these particles there. Now, our wave function, because you're in 2D, right, you cannot move the loop off the particle because you're stuck. So what happens is that you will get an action on this wave function, non-trivial action, and it can be any phase, right? So the particular phase is determines what type of anion. So these particles are called anions, and yeah, you can now add time. You can, when you move in time, you can braid them. You can swap them, and you can swap the first guy and the second guy, or the second guy and the third guy, and so on. So you can do all these operations, and all of those will result in some change, some action on your wave function, which is non-trivial. Yeah. Yes. Right. Right.
Why can't I think of that loop as, say, 10 compositions of little arms? And I do this thing.
Well, I think one loop is just enough. If you do just one loop, you can slide it off and you see it's just identity, so you get boson or fermion.
So I'm saying that the argument that you take
Yeah.
one particle around the other, and it goes, that leads to the identity.
Yeah.
And then break it up going half time.
Oh, that one. Yeah. Yeah. Oh, no. Well, in quantum mechanics, in quantum, you define the wave function in terms of exchange of particles. That's how the statistics is defined. So, yeah. Anyway, I mean, you can have these kinds of operations, but there will be, because of purely topological reasons, there will be certain equivalences. For example, you see this is the path of 3 particles, you know, going along these different paths, but you see that these 2 paths are totally equivalent. If your theory is topological, if nothing changes, as long as you know, because you can take this one strand here and pull it, let's say, down, right? If you pull it down, you get actually this configuration. And since it's in the middle of these other 2, nothing hinders you to pull it down. So these configurations are topologically completely equivalent. And therefore, if you take, let's say, a representation of this move here, of this braiding move, right? So this rho is a representation. I call the representation matrix R. Then these representations have to satisfy these identities, because if you braid 1 and 2, so here you see you have 1 and this is the second one. You braid them, then you braid the first one and the third one. So that's 1, 3 here. You see, and then at the end you braid the third one with the second one. That's here. If you follow the paths, you will notice them. So that's the R2, 3. That product should be the same as this one, which is you braid first 2 and 3, like this is 2, this is 3, and then you do 3 and 1 and 1 and 2. So this is kind of very famous, called the Yang-Baxter equation. It will become important later on. But let me just proceed. So what it gives you, this topological equivalences, give you a group of n strands. It's called the braid group. So this is basically this Reidemeister move. And if they are far enough apart, then they don't talk to each other at all. If you braid them, that doesn't matter. So they will commute. And so this is the structure that you get. But this is, it might look like some permutation group or so, but it's actually an infinite dimensional group, because infinite group, because the sigma I square is not the identity opposite to permutation. So this Bn has infinitely many elements. Now, in this particular example that I mentioned, where you get a phase, these wave functions after many of these operations, if you have identical particles, if you change them in this way or this way, so if this guy goes down or if this guy goes up, you have a different sign. And so this m here depends on the difference, and you get finally this action on this wave function. And for non-identical particles, you can introduce different phases which depend on the particular particle in question. So for example, if this is particle type A, this is B, then the change will depend on some angle, some phase theta AB, depending on the particular combination you take. So depends on your model, and that's kind of what we have here, right? So this is kind of what happens to these wave functions when you exchange these particles in this 2+1 dimensional theories as compared to 3+1 dimensional theories. Now, the interesting thing is that this is just the beginning of the story. So you can actually have something much more interesting, namely, you can have non-abelian representations. That means that's only possible if your wave function is kind of, or your Hilbert space is degenerate. So you have many of these wave functions. And then if you change these particles, your braid group will act in a kind of matrix representation. It doesn't have to be a phase. It can be a complicated matrix acting on these degenerate things. If there's only one state, then of course there's only one multiplication by some C star number or something like that possible. But if you have many states, you can have this type of action, right? Now, crucial thing is that this is non-abelian, because if you have sigma 1 and sigma 2, because these are matrices, they will be, contrary to the story with the phase, or no matter how you multiply them, it's the same. Here is not. So it's kind of a more honest representation of these braid groups. And it's called non-abelian braiding statistics. So there is something non-abelian matrix acting on these wave functions. And the statistics is not only plus minus or a phase. So previously we had just boson fermion, which was plus minus, then we had just a phase. Now we have a whole matrix acting on these wave functions. So this is kind of what this means. Okay. So any questions so far about yeah, maybe this story, this part of the story?
In the 2+1 theory,
Yeah.
the algebra structure of these operators also depends on the topology of the manifold.
Of the manifold, yeah.
Yeah.
So now what I did to simplify things is I'm just taking the manifold to be some R3 or something to make things just simple.
Okay.
Then it only depends on the topology of these strands.
Right. That's
But of course, you can have on top of that non-trivial manifolds,
for example,
topology, and so on.
first picture that you had where the operator, loop-like operator, could shrink to a point. If it is acting on a manifold with curvature, with boundary, even in 2D, it cannot always shrink to.
Right, for sure. This is only in a situation where you actually can. Right?
Okay.
For example, you will have some, pi 1 or something. Or,
right. Okay.
Yeah. So that's any other questions about this? So okay, then what you can this actually connects, this non-abelian property here actually connects to what I was saying before about these 2D lines. You see these lines which we are talking about here, they are actually also defect lines. We can think of them as defect lines in our 3-dimensional theory. So because I mean, this notion of time is kind of in this topological theory is just artificial. So in some sense, you have these lines, and it's topological. The action is topological, so it's a topological theory in 2+1 dimensions. And similar to the story before, we basically uplift the story. So these lines which were stuck on the plane, we now lift them up. Now they can braid and so on, but they can still fuse. So there is still this fusion, and we have these fusion symbols. And they will form a fusion algebra as before. So those things still hold. Now, the crucial thing of this non-abelianness is that this non-abelianness translates to what we previously called non-invertible. Namely, only for these non-invertible lines, we can have non-abelian. We do have these non-abelian representations, right? So that's kind of another thing which is somehow sometimes a confusing thing in the language from when one goes from 2D to 3D. So yeah, this is as far as these lines in 3D are concerned. Now we have of course, before I told you about this pentagon identity of the fusion of these lines. That's still true, of course, because these lines can fuse also in 3D and form this pentagon and so on. That's fine. But you can have more. You can have fusion, and you can have now braiding. And if you now start with this type of picture, which is basically the left and right hand sides are the same, because it's topological, you can pull this strand again down, and you get this picture. So this is just the same, it's equal. But then you can undo all these things and arrive at the other picture by applying this R matrix. So undo this braiding here. You see, now you undo this, the B is now on the left side. You just rotate these two by 180 degrees, these strands, right? So this is the action of these, or you exchange the two particles. This is the action of this R matrix. Then you have the F matrix. You attach this line here to this line. That's what you see here, right? Now this line is attached here. Then you can do another R matrix, which will braid these two lines. That's there, right? Then you can do another F matrix, attach this line here to there. That's well, it's just so this is basically what you have there. And then you can again do the R move, and then again an F move, and you're back there. So this, if you look at it, this is a hexagon. So this is called the hexagon identity. So this is again a consistency of the whole story, that you have to have this identity satisfied. So that is a further constraint which you get in 3 dimensions. Now you can again compute what we called before partition functions. And in 3 dimensions, the way to do it is actually very simple, because these theories I'm talking about are topological. So you suppose you have your R3 here, and you have the world lines of some particles. They are created here, they are created here. They come down, they braid, and then they kind of annihilate again up there, right? And you have actually 4 particles. So they are created here. 2 particles are created here. 2 particles are created here. Then they are braided once and twice. This is this action of the sigma 2. Sigma 2 means braiding of the second strand with the third one. You do it twice, so that's rho sigma 2 square. Now, what does this chi mean? That chi means if nothing would happen, the propagation along time would produce a wave function. From downstairs, you get a wave function chi. From upstairs, you get a dual wave function, also chi. But now this guy, actually something happened, because you have braided them before reaching the time t is equal to 0. You have braided them twice, once here, once there. So the actual wave function is psi, where you have this action of these double braiding acting on it. Then you can pair them again. The pairing of these 2 vectors produces a number. That's what we call amplitude or partition function in this case. So that's, for these topological theories, that's the way it's computed. And it can produce you a link here, or it can produce you a knot or complicated object. And here, for example, you get 2 unknots. Nothing happens. You don't do anything. You just have the incoming state, the outgoing state. You pair them, and you get just this thing. So there are these kind of ways to compute things. It's very topological. Once you know the statistics, you can easily do these types of computations in 3 dimensions. Okay. Now here it's of course another case where you just do. You actually before we had of course two knots if you want, but here we have just one. So if we braid these, so you create 2 particles here, we create 2 particles here, we braid them just once. If we do that just once, you see that the resulting object is just connected, totally connected. So, and similarly here, this is the inverse. So this will give you the partition function or the amplitude of some unknot. So this is how to understand these guys here. Okay, so it's very just pictorial. I haven't given you how these matrices look like, but the rest can be worked out as just algebra. So now another important property is the so-called S matrix, which is a new ingredient. So we have the F matrix, we have the R matrix, we have the pentagon identities and hexagon identities, but there is one more object missing, namely the S matrix. So what does that mean? So consider again the situation where I have a 3-manifold whose boundary is a torus, like on the blackboard. Then I can have a world line of this particle along the cycle of this torus. Inside of it, it will produce for me a wave function. Once I do the path integral on the boundary, it will give me a wave function. If I put the particle, the loop of the particle inside of this torus like this, nothing happens because you can shrink it to 0, it's gone. So this gives you a non-trivial thing, this one not. And now what you can do is you can exchange A and B cycle of the torus. This is called the S transformation for people who are familiar with modularity. Then the particle will go actually along this line. So that means that you have actually done some cutting and sewing and so on. You get this kind of picture. Now, if you had 2 particles, J and J prime, and you act with this kind of transformation along one of them, then they will, at the end of this operation, when you exchange for one of them the A and B cycle, they will form a Hopf link. And moreover, what happens is that this will be a Hopf link in S3, because you can think of the solid torus and the dual space. I mean, the complement of it is again a solid torus, and you glue them together, you are actually in S3 or R3 with the boundary, and you have this link here. So what it means is that the action, the modular S action on this wave function, its representation, can be computed by computing the partition function of this Hopf link. So this is mathematically denoted by taking the trace of doing one braiding operation here, another braiding operation. This is the R matrix, right? And then this, you see this produces for you this Hopf link, and that just means, and that's in S3, and that computes for you this type of object, which is the S matrix, which acts on these wave functions, on these boundary wave functions when your boundary is a torus. So this Sij is basically acting on anion types I and J, which are running along these lines here. So this Ai and Aj are basically type of particles or type of lines, if you want, in your algebra, and you braid them twice and take the trace, and you get this S matrix. So this is yeah. Any questions so far about the story? Okay, so now there is one more object, a T matrix for modularity. So this is just identity matrix times this theta. This theta here is what is called kind of the twist. And it's now I go to some mathematical jargon. So this forms a braided tensor category. So it has to satisfy certain consistency conditions with the braiding and so on and so forth. And also some duality constraints. So the twist of the dual object is the dual of this twist and so on. And then, so this T matrix with this particular twist satisfying all these properties together with the S matrix before, then basically forms a projective representation of the modular group SL2Z acting on these wave functions, boundary wave functions for the torus. And that's kind of important, that this whole structure here gives you, together with these R matrices, everything which we had before, gives you the structure of what is mathematically is called a modular tensor category. Now, what one can do more is that one can have, of course, these lines, right, in 3D, but one can also have certain surface defects. So one can have a certain, that means that whenever this line pierces the surface, or let's say you start from here, it pierces the surface, it gets transformed. So there is some group action or something like that associated to the surface, and there is a representation of that group acting on this line. So you enter the surface, and on the other side you are different. You get a different line. So it's now more and more abstract, and but you can easily picture picture what is happening by using these geometric tools. So that's kind of what is known as a surface operator. Now these surface operators can by themselves also intersect. So they can form such group laws or more complicated stuff. So they can have this kind of surface operator here, G and H, and you can have even a line at their intersection, and you get a third guy, which is just given by the group law in this particular case. So you can have all these objects in your 3 manifold, and you can compute partition functions, and you can get very interesting. You can get very interesting structures and so on. So where we are also exploring these types of structures. I won't go into details how to obtain them. There are of course many different ways to do that. But before coming kind of to an end, I wanted to to give you actually concrete examples, because I have given the talk was kind of abstract. I have drawn you some pictures. I told you that in 3D we have these wave functions, but how do they look like? Let's give you some concrete mathematical formula for these wave functions. So that's what I want to do at the end. But before I go to that, any questions about maybe these type of structures or the things which I explained before? Okay, then let me just give you some examples. So, well, these wave functions. So this is now some physics notation. But this wave function here can be computed in physics jargon in this kind of Liouville conformal blocks. You have these kind of integrals over some cycles here, and the integrand is the exponential of this kind of function w here, which kind of has this structure. And these w coordinates you integrate over, the z coordinates are the actual positions of your particles. So you see you have these particles. Let's say in this case it's a torus, in this case it's just a sphere. They end on certain points. These points are z for particle A, it's ZA points. They're basically numbers on the complex plane. And these other guys, these w guys, are integrated. Once you do this, you will get a function, or actually a section of a bundle, more complicated, depending on these z's. That's your wave function. And you can have, these wave functions are degenerate because you can have many different integration cycles and get many wave functions. It's a vector, actually. And you see this is called Coulomb gas representation because in 2 dimensions, this is just the Coulomb potential in 2 dimensions. So you can think of these as particles subject to a Coulomb interaction. And yeah, that kind of produces for you, once you think of them in this way, you actually are doing some kind of statistical integral here with this kind of Coulomb potential, and you get your wave function. So that's one way to think about these things. And you can also have what we more recently have been doing. We have introduced irregular operators, which have not a logarithmic potential, but some polynomial potential. And you get these kinds of structures. So at the end, these functions, these wave functions look like these kinds of integrals. And yeah, then you can show that actually you can take your wave function psi, it's a vector, as I said, and this psi satisfies these kinds of fancy equations, which are called KZ equations or generalizations. And from these kinds of equations, you can actually deduce all the braiding properties, the R matrix, F matrix, and so on. In particular, one corollary or theorem of this representation is that, well, they have irregular operators here. That's why there is this constant term. Whenever you have that in differential, partial differential equations, you have so-called Stokes matrices. And the Stokes matrix basically translates to the R matrix. So the Stokes matrices have to satisfy the Young-Baxter equation, and they do. So that's kind of one thing where things are getting concrete, but then also more complicated, as you see. So one has to digest this more. But just wanted to show you these formulas, what you get at the end of the day, and with this, I would like then to end. Thanks.
Questions?
Hi, Babak. Very nice talk. So I have a question. For this wave function, so from this wave function, you can get R matrix and F matrix.
Yes.
Compare with solving the Haghighat equation. How hard is it? Is it easier to use this wave functional to find this R matrix?
Well, in this particular, it's not so easy. You have to still do some work. You have to deduce these these Stokes matrices. But once you have this structure, you can also do that. And yeah, so that's just, yeah.
Thanks.
More questions? So let me ask you some very naive questions. Often in algebraic geometry, when you have a category defined on a space, you go one dimension higher. Your category embeds normally in the category of similar objects in one dimension higher. When you come back, either you get the same object back or you get extra information, which tells you the subspace, how it deforms in the ambient space, and what does that imply for your object.
You have the same structure here.
This is my curiosity. Here it seems like something very weird happens because, like for instance, if you do 2 + 1 TQFT, and in the situation where your loop going around two particles gives you an angle, phase,
Right.
but if I embed this thing in 3 + 1 TQFT, I can always go around.
In that sense, okay.
So it gets even more simple.
No. Well, you cannot directly translate the structure in that way, but there is something which is called a higher category. So if you go to higher dimensions, you can have, these lines, these surfaces, other codimension defects. And those structures, can themselves have kind of fusion symbols or F matrices and so on. But then their fusion symbols and F matrices actually become lower dimensional categories by themselves, until you reach the point where they are actually the junctions are just points, and then they are just numbers.
So if I go to higher dimensions, I need to have higher dimensional operators.
Sure.
Defects.
Yeah. You get also higher structure called higher categories. Yeah, but so far we are not going into
another question is, if you're applying this to a manifold, compact manifold with boundary, let's say for surface defects, your algebra structure, a fusion structure on the surface defects, it seems like absolutely implies something on line defects. Because the surface defects, now the surfaces have boundary, and the way they interact,
you mean this
structure on the boundary line up.
You mean
Am
this
I
kind?
right? Yes.
Yeah.
Is this true?
You can have a line there as well. Yeah.
So I'm saying, like, if these are boundaries of these surfaces, then those are line defects, right? Those three lines, like a Mercedes logo up there, I can think of that as two line defects. So they have their algebra structure. Lower one has algebra structure.
No. Wait, you mean the point where they all are meeting? Only at that point, yeah. You can put a line defect, but otherwise you have to think of them as extended. So they maybe they go all the way,
So can I calculate partition functions of interaction between surface defects from its boundary line defects?
Well, the surface defects are another type of information on top of the line defect. So you basically need all of them to compute them.
So it's extra.
Yeah.
Okay. Any other questions? All right. If not, let's thank Babak again.
For me.